So one of the things that we're after as geologists studying sediments and ice in Antarctica is to try to figure out how the past changes that occurred before humans were one of the prevalent forces on Earth, how these changes occurred, how fast they occurred, and how frequently they occurred. There always has been climate change. That's a well-known fact. We geologists are the ones who've unmasked that. But we're also interested at looking at the human timescale and how the changes that we're observing now in the instrumental record of sea level, of temperature, of the amount of CO2 in the atmosphere relates to what we can pull out of ice cores and sediment cores in Antarctica. And Antarctica holds many secrets because it's the last really big ice-covered part of the world that can contribute to really big meter-level sea level rise. So what we're looking for as geologists is to go back in history and see how often, how much, and perhaps why sea level has changed in the past by looking at the sedimentary record as well as the ice core record.
I think in order to understand where the ice might go in the future, we have to understand when it got here, how it got here, and then periods of ice advance and retreat. So when you have a continent that's almost completely covered by ice and all that ice has the potential to melt, you certainly want to understand its history. So for me, that's one of the big draws of coming to Antarctica, is that there's so much to learn about a place that really matters.
Once in a while I get to go to meetings. We never thought. And it's so, like, going to those.
SALSA, which stands for Subglacial Antarctic Lakes Scientific Access, is a pretty unique and interdisciplinary project where we're bringing biologists, geochemists, geologists together to try to tap into this pretty unique environment of a subglacial lake.
A subglacial lake is any lake that is underneath a glacier. Under the Antarctic ice sheet, there are hundreds of subglacial lakes, and very few of those have actually been sampled. So we're going to be going out to a lake called Subglacial Lake Mercer and drilling through the ice into that lake.
Lakes anywhere on Earth are reservoirs of history, right? They're on the bottom of everything. We'll learn a lot about the history of Antarctica in terms of when the ice cover was here, when it was not here, and that tells us about past climates.
Well, we're drilling. At least we get down a ways before we can, then I don't care if we slow down.
This project revolves around a borehole, and the borehole is drilled by our fantastic drillers. And they're basically using melted snow that they're heating up and putting through a shower head that will melt the ice and snow around them to make a hole. And they're going to keep going down, 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 all the way a kilometer through the ice sheet. And that's what we'll use to access the subglacial Lake Mercer. So we're going to enter the borehole with a device called the multi-core first, and that's designed to sample just the interface between the lake water and the sediment. And that weighs about 150 pounds, and it fills 3 tubes with mud at a time. So when it comes back up, hopefully we'll have 3 tubes with a good amount of mud in them that we can then study that interface with. It's 1069, that would be 3 meters below the ice surface.
So once we open up the borehole, pretty much the activity is nonstop. And it's like a a machine or a play where everybody has this role and they know exactly what they need to do. And people do that for a day, and then a second day, and a third day, and a fourth day, and a fifth day, and a sixth day, all mostly without sleep.
Jack got mad at me. I said 3 cores, 45 centimeters each.
One is a little shorter.
3 cap cores.
Woo! Yes. Subsequent to that, we're going to use something that we're calling the borehole jumbo gravity core. And it's going to go down into the borehole. It is about 2,500 pounds all put together. And basically we have to lower the core into the borehole until we get close to the bottom. And then we're going to send something that we call a messenger down. And the messenger just clips onto the rope and we just let it drop. And it goes zooming down the rope, and it's going to smash into something at the bottom of the rope and allows the core to free fall so that we can really punch into the sediments.
Go, devil. Oh, there we go. That worked, baby. That worked. That was 2 minutes. Yeah.
West Antarctica for over 30 years has been anticipated to be the least stable part of the Antarctic ice shelf, in that because the ice is grounded below sea level, that if we warm the oceans around it and the atmosphere on top of it, that we could potentially have catastrophic melting that would then enter the ocean and cause sea level rise. So one of our interests in trying to core deeper into this type of sediment is that as these sediments are deposited in a perfect setting, they would be deposited as if you could imagine a layer cake, one layer built on top of another. And as you move up in those layers, you're getting into younger and younger sediment until you get to the surface, which is more or less present.
Let's balance it on the railing. This one's really heavy, guys.
Let's lower this in. Let's lower this. You guys went to the shoulders. Fun trick. Don't tell the guy in front.
They're gonna do some good cutting.
There we go.
What a cut.
Oh, wow.
Give it some
Let's
more.
go 33.
33. 33?
Yeah.
33.
It's somewhere between 170 and 180 because there's some empty space here.
Okay.
Did we win?
What was you want a Pop-Tart, Amy? Or maybe some Fruit Loops.
Am I hearing some sarcasm?
One thing that's unique about this environment is that West Antarctica used to have seas across it. At times when the West Antarctic ice sheet was not there, at warmer times, this was a marine basin. And this is where I come in with my science and that of Amy Leventer of looking at one-celled fossil algae called diatoms.
A diatom is a single-celled algae, so it's photosynthetic, and that means that it can only live in the uppermost part of the water column, and so it's telling you things about the upper ocean. So there are two big things that the diatoms can tell us here. One is it can tell us something about the environment, so whether there was different environmental conditions. The other thing they can tell us is they can tell us about the time that it happened. And so one of the big things we want to see here is when were marine waters extending beyond the grounding zone, and this was an open seaway. The other thing that we can see is what's under the Antarctic ice, and that should be eroding out from the bedrock and into our site.
And
There it is.
You found the Simonsenii?
A piece of a Simonsenii. Actually, I always called it Simonsenii. I do consider the kind of science I do no different than an historian, and a history professor may look at ancient books, ancient archives, going back page by page, and I do that by going back from the topmost sediment, which was deposited yesterday, and then back through time. Each layer is older in time. I know I described myself as working with the diatoms, that's one language, but there are lots of other languages. And so in some ways we're like this big team that each of us speaks a different language, and then we figure out the whole story. I feel like my contribution is helping us understand climate, deglaciation, how does the world work, and trying to provide enough information to convince people above me or in a different bracket that this is real. We're just, again, reading the history book and telling them this is how it works. The exploration that we're doing is that because there's a goal beyond ourselves. So we do have adventure when we're out there, but always above that adventure is the mission, which is the science. I think the most impressive things for me is we don't see each of us as individual scientists. We all have one big mission and this idea that the whole is bigger than the sum of the parts.